Hey folks, so this video is going to be about 68K assembler stacks. So we're going to start with just a bit of code. We're going to move the byte 7 on top of the stack, so that's a pre-decrement. So this kind of command here is going to add the number 7 on top of the stack. So to visualize it, we got our stack here. 7 is going to be down here now. So if we execute our code, okay, execute, nothing's going to come out obviously. But if we go to view and then stack, we'll see that the number 7 is in our stack. Now the address register 7 is the same thing as your stack. Using SP is just for notation. You can use any of the address registers as stacks too, but you may have to use the link command. But I won't talk about that really. All you really need to know is that your address register, that address that it contains, points to your stack. So we can see here, this is, I can't really highlight it, but this address here is the start of our stack. So we got 07 there. So if we were to put in a word of, I don't know, 78. Remember that this is all in hex. The stack records in hex. So 78 in hex is 4e, so we should see a 4e in the stack. We'll close that, execute again. Bingo, we got a 4e in the stack now. So that's good, that works. That means that now we will have 4e here. So you could say that the pre-decrement is pushing onto the stack. So post increment would be popping. Okay. So let's try and pop number 7. So at this point we should know how, just like how the stack data structure works. So if we want to pop number 7 but 4e is on top of it, we can't just kind of ignore 4e and go right for the 7. We could, but it's not good practice, you know, it's not how you use the stack data structure. So we have to pop both 4e and 7 if we want to get to 7. So let's type that out. So we want to, we're going to shift our popped values into data registers. So let's pop, we gotta pop 78 first, so we'll move SP plus, so that pops, and that returns the pop value, so that will pop into, let's do D2, so that'll pop it to D2, and then we want to pop our byte next, so again, okay, like that, and we'll put that sucker into D3, just like that. Put a space there. Okay, let's run that and see what happens. Okay, execute. Okay, play. Alright, perfect. So 4e is in register 20, exactly like what we wanted. That's 78. In D2 rather. I'm a little tired. And then 7 is successfully saved in D3. Perfect. So that's good. That's what we wanted. So now when we're done with the stack, we want to shift our stack pointer. Our stack pointer is kind of the thing that moves up with our stack. So if we add 7, then our stack pointer will be here. Then if we add 4e, then it will move up again, and it'll be here. So when we're done with the stack, we want to shift the stack pointer back down to the bottom of the stack. So the way that we do that is we add onto the stack pointer directly. Okay, so we're familiar with the add command, so let's just do add W for kicks. And now we have to look at how much space we used up with our stacks. Just sorry, moving some clutter. Okay, so our number 7 is a byte. Now our the top of the stack is always byte 0. So for 78 we used word. Word is 2 bytes. So that means from here to here is 2 bytes. So that means, I'll go over indexing in a second, but that means that 4e is 2 bytes. So we go from 0 to 2, then 7 is actually just 1 byte. So that means that the very bottom of the stack is byte 3. So we use 3 bytes, which means that we want to add 3 onto our stack pointer, and then the stack pointer will shift from the top to 3 bytes down. Okay, so we add 3 to our stack. Okay, let's run that, see what happens. Okay, so our registers are good, and we can see that A7 is no longer pointing to the proper stack address, so that's a good sign. So if we look at the stack, so our stack pointer is currently shifted downwards, which is good. So that means that if we start pushing onto the stack again, it's essentially going to overwrite the elements that are there from before. So it doesn't delete them per se by adding 3, but it just makes it so that that space can be overwritten, which is exactly what we want. It's good. So let's go over indexing now. Let's say I wanted to access number 7. Okay, so as we can see from our little table, our little stack on the other side, if I want to access number 7, you always look at whichever byte number is at the top of your stack block. So this is a stack block. Whoops. This is a stack block here. So you always want to look at the top of the stack block. So here, if you want to access 4e, you would use index 0. It's kind of like a list, right? So if you want to access 4e, you would do 0 SP, and that would return the contents of the block at byte 0. So if I want to access 7, I have to look at the line above. God damn it! I have to look at the line above 7, which is at byte 2, which means that I can do index of 2 and check SP. So let's try that in code. Okay, so let's shift those out of there. We don't want that anymore. So let's move. We're moving a byte, and we want to access 7, so that's 2. And let's move that into D1, and just for shits, let's print it. So I actually don't need a thing there if we're doing a print command. Easy68K defaults to Word, so if you just do move without a size specifier, it'll just default to Word. Okay, so we move number 3 to D0, and then we'll do our trap 15. Okay, so that should print number 7. That's what we want. Alright, so let's run this shit. Okay. Bingo. We're all good. Sick. Okay. So that's indexing, and that's really important because now we're getting into the witchcraft. Now we're going to start dealing with subroutines. So I'm just going to make a subroutine called sub_r. And here we are going to jump to sub_r. And what jump does is it kind of acts as like a function call in a high-level language, where it'll go through all this code first. So, oops, it'll go through all that code first. And then once it hits the jump, it'll go to the subroutine, do it, and then come back and fill in whatever is down here, whatever that code is. So it'll just resume where you left off, and that's really nice. So let's take a look at how that works and how the stack changes in a subroutine. So let's put a print command underneath our JSR. That'll just print D1. So number 3, move that to D0, trap number 15, and we can't forget our good practice of resetting the stack. So we will add, we add 3, we add that to SP. Okay, so the idea is we're going to take, let's take 78 this time. We're going to take 78, we're going to print it out, but from the subroutine. So we're going to shift 78 into D1 within the subroutine. But this is where things get just annoying. Okay, so there's something called the program counter. I'm just going to cut out for a second. I'm going to clear some room on the drawing page. Now the way that we're able to resume after a jump, a subroutine jump to that code, is via the program counter. So when you shift to a subroutine, what happens to your stack is that a program counter gets added on top, and the program counter is effectively just an address, and an address is long, or 4 bytes. I hate it when it does that. I need a new tablet, I think. So that means in start, in that part there, our stack does not have a program counter, and it starts at byte 0 at 4E, and it's all good just like we saw earlier. But when you add the PC on top, suddenly all this stuff gets shifted around, which is really annoying. So you have to really keep track of your program counter. So now we have 0 up here, 4 here, because our program counter is 4 bytes. Okay, and then our 4E is a word, so then it goes down to 6, and then 7 is still a byte, so the bottom of the stack is just byte 7. So now theoretically, if we wanted to print 4E, our index would be 4 SP. So let's give that a try. Alright, so 78, which is what we want to move, or 4E in hex, is word, like we specified above. So we want to move a word. We're moving the word at 4 to D1 so we can print it, and then use RTS, and RTS stands for return to sender, and that will send us back to underneath the JSR so we can resume. So what we should get is a printout of number 78, which is our top inserted item in the stack. And there we go, we got 78. So that's pretty much it. When you return to stack return to sender, the program counter gets popped again. So you don't really have to worry about adding 7 bytes when you're resetting the stack. You still just have to add 3 bytes, essentially, right? Now if you were to add something else on top of the stack within your subroutine, that's when things get a little tricky and you kind of gotta hack around a bit. So your program counter is going to stay in the same spot. It's not going to shift up for you. So if you wanted to say insert, I don't know, number 4 onto the stack, then it would appear up here, okay? And suddenly all of your byte indexing gets screwed up again. You end up with 0 up here, and since we used word, it's 2, then our address is 4, so that's going to be 6, and then we used another word, so that's 8, and then a byte, so that's 9. Now if you wanted to shift to another subroutine, you got to make sure that your PC is on top. So if you had, let's clear up some space here. If you had sub r like that, and sub r calls sub r2, you have to make sure that your program counter is at the top. So I'm going to cut out for a second. I'm going to write some code that shows all this. Okay, so at the time of this line, so right after this line happens, this is what our stack looks like on our right here. So our program counter is buried. Now if you don't shift the program counter, if you don't shove it back to the top of the stack, you will not be able to do another jump, because since we're only dealing with one stack here, you really have to make sure that your program counter is at the top so it knows where to go back to. So what you can do is kind of a bit of a hack. I'm not sure if this is proper practice or not, but it does work, which is the important part. So remember that addresses are long, which are 4 bytes, so you have to do move long. And if we're looking for a program counter is at byte 2. So we take that entire block and we put it on top. So after that highlighted line on the left happens, our stack will look something like that. I'm not too sure if this program counter gets eliminated or not. I don't think it does, but the important part is that our program counter is now at the top. That's what we want. So now we can jump to subroutine 2. All subroutine 2 does is prints the number 1, that's it, and then it will return to first subroutine. So let's go through this. So we have jump subroutine here. This goes to sub r. Okay, so we put 4 onto the stack, we move our program counter to the top of the stack, and then we jump to subroutine 2. So now we jump right away. Here's subroutine 2. Subroutine 2 will just print the number 1, and then it will return to its sender. So that means that it will start doing stuff after this jump, which is just the original return to sender. So it kind of follows the ladder back up again, and now it'll start resuming this stuff. So what we should get in our output is just 1, 2, no new lines or anything, so technically 12. You'll get a printout of 1, and then immediately after the 1 you'll get a printout of 2. So let's execute. Let's play, and that works swimmingly. There is an error down here. I'm not too sure what that means, which makes me think that the program counter shift is not good practice. But this does work, so take it with a grain of salt. The important part is that you know how the stack works. So hopefully that was helpful. Tongue twisting here. Feel free to subscribe. Apologies that the video was kind of long, but it's a bit of a confusing concept, so I do hope that the length helped out at least a bit. So yeah, stay tuned. I'll have more videos coming soon. Thanks for watching.